What's up, nerds? Today we're going to talk about modeling with quadratic functions, and specifically, how do quadratics kind of function in the real world? And first we're going to look at what happens when the data we collect is perfectly linear or perfectly quadratic. And something really cool happens, a really neat pattern forms, as long as we've collected data with equally spaced input values. So those are going to be my x values. Maybe we're using a different variable. But if we look in example 1, we can see that these inputs go up in this first example. In this first example, these inputs go up by 1 each time, right? Plus 1, plus 1, plus 1. And that is constant. So I have equally spaced inputs. We don't necessarily have to go up by 1. Looking at example B here, right? We're going up by 2 every time. But as long as that is constant, then again, this really neat pattern forms. So what's that pattern? That pattern is going to involve either the first or second differences of the data. And what I mean by that is kind of looking at the same pattern we just saw for the x inputs. I want to figure out what am I going up or down by for each of my outputs or my y values. Okay, so looking at example A, I can look at these two, and maybe you can look at that and tell immediately, okay, I can tell I went up by 1.5, right? But sometimes decimals are a little bit sneakier. They're not as easy to point out. And here comes why we call them differences, because we can always take the second input value, or I'm sorry, I guess that's the output, the second output value, and subtract the first output value from it. And that difference, 8 minus 6.5, is actually how much I went up from x equals 1 to x equals 2 and those corresponding outputs. Okay, so let's go ahead and do that again. So I can, again, show that work for the difference. If you can do it in your head, you don't have to show the work. So 8 from 9.5 is going to be a positive 1.5. And again, I'm going to go ahead and do this one in my head. To get from 9.5 to 11, I would add 1.5. Okay, and since I only had to go like one level down in the table, we call this the first difference. Sorry if you can hear my dog panting over here. So that first difference is constant, or it's the same every single time. And I can see from my table above that if I have a constant first difference, then I know that this table models perfectly linear data. Okay, so let's look at what a second difference means then. So in table B, change my variables, but the input's still on top. My input's still t. My output, remember we always subtract the second term minus the first term. And we get the fact that the table is going down by 5, which again, hopefully that's pretty apparent. You can see to get from 9 to 4, we go down 5. Okay, well, interestingly, to get from 4 to 1, I only go down 3. And then from 1 to 0, I only go down 1. So that's my first difference, but it's definitely not constant. Those numbers are not the same. So let's go ahead and do another level of this table. Let's go ahead and look at what this difference is. And maybe dealing with negatives, you're not as confident, so let's actually do the difference again. We can do -3 minus -5, and we get +2. -1 minus -3 is also +2. Look at that. So I would consider these to be my second differences because I did a second round of finding the difference between each of those output values. Oh, I don't know why I put seconds. Okay, so those are my second differences. Since it's the same, we consider that to be a constant second difference. So I can tell that this table models perfectly quadratic. Okay, so go ahead and pause the video here and see if you can do C and D on your own. Righty, hopefully you pause the video real quick and we can see that we were, well, first I guess we should always check, were my inputs equally spaced? And that they definitely are for this problem. Okay, and I've never seen this pattern before. I added twice, but I subtracted once, and that's really interesting, but let's just trust the process. So it's obviously not linear. So then let's go down a row, and if we need to use our calculator, right, 1.3 minus 3.1 is minus 1.8. Minus 1.8. Look at that, a constant second difference, which means C is definitely quadratic. And you might be able to see D without even writing it down. Again, always check to make sure that that data is equally spaced. So my inputs are going up by a half each time. So that checks out. And I am going down 2 every time. So that is definitely a constant first difference, and this is going to be linear. All right, so what happens when my data isn't perfectly linear, perfectly quadratic? Well, it's not necessarily going to show a pattern of constant first or constant second differences. So that's where we have to rely on the graphical appearance of the pattern. So we can go ahead and plot all of our data in a scatter plot, and hopefully it's pretty apparent looking at this that this generally forms a U shape, this generally forms a linear shape. Obviously it's nowhere near perfect, but it gives the vibes of a quadratic or a linear function. So A, we would definitely want to use a quadratic model, and B, we would definitely want to use a linear model. Okay, and then the question is, how do we actually write an equation? Because if it was perfectly quadratic, we could use standard form, vertex form, intercept form, any of those to help us like build the function. That's not going to be as easy when our data isn't perfectly aligned. So we can use our calculator, just like we did for linear regression, to create a quadratic regression. And it's the same exact steps. Literally the only difference is that when we are, after we've entered our data, we're just going to choose a quadratic regression instead of a linear regression in our calculator. Okay, so I've done a lot of that for us because I don't want you to have to sit here while I enter data, but please pause the video at each example. Make sure that you type in the data and get the same values as me. And if you don't, double check with me. I very well could have made a mistake, but just make sure you entered the data in carefully as well. Okay, so in this first example, NASA employee designs a model airplane, flies in a parabolic path. Well, that's super handy to know. It tells me to use a quadratic because we know the shape of the quadratic is a parabola. Okay, so I don't even have to map this out. I wouldn't have to check for second differences. I just did because I thought it was interesting that this does end up to be perfectly quadratic data. Okay, so this table shows the height after t seconds. I typed it in my graphing calculator. I created a quadratic regression, and it uses the wrong variables in my calculator. So I just want to go back through and rewrite this using h and t. So h of t equals negative 0.9 t squared, right? Because t stands for time. So it just gives us a little more context and helps this equation make a little more sense when we're using it. Okay, so now I have my function. This is one of the things it asked for. Okay, and then it says approximate the height of a model airplane after 6.5 seconds. So I know that 6.5 seconds is a time, so I'm definitely gonna plug that in for t. Okay, so I'm gonna go ahead and do h of 6.5, and remember function notation, this reads, what is the height after 6.5 seconds? Or what is the height when I plug in 6.5? I'm gonna make that look a little better. Okay, so when I plug that in, remember that you can use that shortcut in your calculator. I'll talk about that in a second, but just as far as showing work, right, this is one way that you could type it in your calculator to find the answer. And we type that in and you get 3.975 feet, because we're talking about height. Okay, so remember another way you could have calculated this without having to do all that work to type it in the calculator is when you run the regression equation, right? So it's like in this step up here, when you're just creating it for the first time, remember we can store your regression equation in y1. And remember the way that we get to y1 is alpha trace. So it's the alpha button, that green button. Oh, I guess I'm not going to write that down because you know what? I have it written down for the next problem, right? Okay, so alpha trace is going to give you that y1 variable. And then you run your quadratic, you get the quadratic out, and then you can use function notation on your like blank calculator screen. So click second quit, go back to the blank calculator, and then you can just do y1 of 6.5. So it's exactly the same as what we did here. We used function notation. We just can't use h as a function in the calculator. We have to use y1 as a function in the calculator. But you type that, and as long as you have that regression equation stored, your calculator again will tell you, wow, the answer is 3.957. Nope, it is 3.975. Okay, you get it. Okay, so example 2 again. Please pause, see if you get the same regression equation I do. If not, double check your data and then double check with me because I might be wrong. Not too proud to admit it. So, table shows fuel efficiencies of vehicles at different speeds. Write a function that models the data using this equation. Okay, so let's make the equation first. Type in all of our data. Let's go ahead and store this regression equation. And we get out this model. And the great news is they're using x and y as their variables. So we do not have to change that from the calculator. So I'm going to go ahead and box this in as my answer. And notice that when I wrote this down, I did not round. I said I'm still going to use the whole long number. And so it's actually really important on this problem that you store the regression equation, because we do not want to use rounded values in further calculations. Right? It's going to create error in my data, and we're going to talk about that in the next part of this example. Okay, so now that I have that regression equation, it says use this equation to find the speed that results in the best gas mileage to the nearest whole mile per hour. Okay, so best gas mileage is going to be, gas mileage looks like it's my y value. So I want to know the biggest y value, which hopefully you're starting to make a little connection here. This is what I can call my biggest y value. That's going to be my maximum value. So this is something we're definitely going to have to do in the calculator. And I'm going to have to show you how to do this in class. Because there's a trick to find the maximum that I haven't showed you yet. So we will definitely go over this. But for now, you can look at the graph on your calculator and you probably won't be able to see much. So you're going to need to change your window. So if you click the button at the top that says window, you can see it says X-min, X-max, Y-min, Y-max. And that is telling you X-min, What's the smallest x value you want to see? X max. What is the biggest x value you want to see? Y min. Nope, this is Y max at the top. Smart, smart, smart. Okay. Okay, and so looking at our data, my x's definitely go up to 72. So maybe we want to change it to like from 0 to 75. And maybe we need to play around with this. You're not always going to get a perfect window the first time. Okay, and then for your y min and y max, I definitely don't have any negative y's, so maybe we can do 0 for my y min. And y max, we can look at the biggest number. Biggest number looks like it's under 30-ish, so maybe 30. And go ahead and click the graph again. You should see the graph a little better. If you can't see the whole graph, play around with those numbers. Do you need to make it taller? Do the x's need to go farther? But from this, you can kind of generally judge where is that maximum. Because that's really what the question is. It's find the speed. The answer is going to be the speed that matches that maximum y value. Okay, so looking at your graph, hopefully you kind of see it's around 50 miles per hour. It's actually going to be 51 miles per hour. And again, I will show you in class how to find that exactly, but it's going to be 51 miles per hour. And notice you didn't have to type that equation in because we stored it into y1, so it graphed it for me. Okay, so rewrite the function with coefficients rounded to the nearest 100. Let me go ahead and erase my table over here. Okay, so let's go ahead and rewrite this. When I rewrite this, y equals rounded to the nearest hundredth, negative 0.02 x squared plus 1.55x minus 10.86. Okay, and now I want to answer that same question. Well, the good news is, as long as I understand that best gas mileage is best or biggest y value, and I know that that's going to be a maximum, I can go ahead and use my standard formula to find the x value of the maximum, right? So we can do x equals negative b over 2a, and that's way easier than what we had to do with the calculator. The issue though is that it tells me that the answer is 39 miles per hour, which is way different than the picture on the graph. And let's actually look at that in the table. It's telling me I get the best gas mileage at 39 miles per hour. Well, I can see in the table 42 miles per hour, I'm getting 27. 47 miles per hour, I'm getting 28. 50 miles per hour, I'm getting 29. There's no way that 39 is the best gas mileage, or 39 miles per hour gets me the gas mileage, because I can see on the table it's definitely closer to 50. So it's kind of concerning, and the reason that happened is because we used rounded values in our calculations. So that's a big idea, and again, don't worry about the first part, we'll go over that in class together. Okay, and example 5. We have an ACT practice problem, but it is legitimately just making sure we can type that data in. On ACT and SAT, we will have Desmos, and so we will also practice that in class to make sure that we know how to use that to do a regression equation really quickly. So anyways, in Desmos, we get that regression equation, and we can store that. It asks, ball is tossed, quadratic equation, According to the regression equation, what is the maximum height? Well, the cool thing is, just telling you, I know we haven't learned it yet, but in Desmos, it'll graph this regression equation for you, and you can just click on the maximum, and you can see that the maximum height of the ball is 22.4. Okay, but what if that's not an option? Well, then we can use, for maximum height, we first have to figure out where that maximum happens. So we can do x equals negative b. And I'm just going to type in quite a few sixes. There's no way to say repeating 6 in your calculator, but we can do a lot of them and avoid that whole error using rounded calculations thing. So I'm just going to type in a bunch of 3s. And we get a number. And remember, I don't want to use rounded values, so I'm going to keep as many as I can. But here's another cool little shortcut, is instead of having to type this whole decimal out again to do my next calculation, we can store this value as one of the letters on your calculator. So it's the store button, and then you're going to click alpha math for A. And so it's literally going to say like store, or I think it's going to look like this, answer store as A. And then we can plug it in just using that letter A. We can type in y1 of A equals, and it's going to give you 22.4 feet. Alrighty, so I will see you in class, and we will talk